When we talk about collision theory, we're really talking about the theory of why chemical reactions happen the way that they do and at the speed that they do. And in order to understand complex theories, what we often do is create a model. So think about the Bohr model of the atom was really just a way that we could visualize and understand the way that the atom is actually structured. I have my own personal model for collision theory to help explain it. It's what I call the kindergartner model of collision theory. To understand it, you need to imagine a box, a room, and inside that room, it's filled with kindergarten age children. Those kindergarten age children, like atoms, have the tendency to run and move randomly with no thought or care for others around them, bouncing off of objects and continuing with random movement. Once in a while, this is going to happen where these two kindergarten children will actually collide with each other. And if they collide with the right energy and at the right angle, they will fall down, get injured, and cry. That is much like a chemical reaction. When you have the collision of two atoms changing into something different due to the amount of energy or the angle that they hit at and changing into a new substance, it's just like my kindergartner model. So I'm going to be using the kindergartner model to help us understand ways that we can change the rate of a reaction. So the first thing we have to do is we have to fill our room with kindergarten children. So there are many ways that we can change the rate of a chemical reaction. And the most obvious one is probably temperature. When you increase temperature, you increase the speed that particles move at. And when you increase the speed, you increase the amount of times they collide, and you increase the energy of those collisions. I think of an increase in temperature the same as giving kindergarten kids or kindergarten age children sugar before they head into an enclosed space. Right? They're going to be running around, moving extremely fast, and colliding more often. When they collide more often, they are actually going to collide harder because they're traveling faster. This will end up in an increased number of collisions and an increased rate of reaction. So increasing temperature speeds things up, causes more reactions to take place because it causes more collisions and it causes more energy in those collisions. Now, you can also change some other things. So if we actually think about some of the variables that we can manipulate in here, one thing you might be thinking about is concentration. If you were to have the exact same size of space, but increase the amount of kindergarten children in it, when they start moving around, there is a much greater chance that they are going to collide with each other and get injured, right? 300 kindergarten children in a gym versus 3 in a gym is going to end up with many more tears. So it is going to cause an increase in reaction rate when we increase the concentration. So I always think of concentration the same way that I think about the number of children. More children collide more often, less children collide less often, more children, faster rate of reaction, less children, slower rate of reaction. So that's what we can do by changing the temperature. There are some other things that we can also do, and one would be to change the pressure. Now, in order to understand a change in pressure, I'm going to draw another diagram so that we can take a look at how that would affect something. The way that I like to think about pressure is to think about a piston. So imagine a chamber and a piston that can slide upwards. When you push that piston upwards, what you're really doing is causing an increase in pressure. The other thing that you're actually doing is causing a decrease in volume. To show you an example of what that looks like, think about the amount of space that you have in this chamber versus when you increase the pressure and push that piston upwards. What you're really doing here is you are giving less space for the molecules to exist in. The same number of molecules would exist in the other piston chamber, but they have less space to actually work. So causing this push upwards is an increase in pressure, which is actually the same as a decrease in volume. But we can also think about this going the other direction, where you can have a decrease in pressure. A decrease in pressure is actually the same as an increase in volume. And it's all due to the changing of how much space is available to those particles. So now that we have a visual of what pressure and volume actually look like, let's take this back to our other example and see how it affects our kindergartner model. So here we're back with our kindergartner model, and what we're going to do is we are going to increase the pressure. To increase the pressure, that's really the same as giving less space for this to take place in. So what we're really going to do is take the same number of kids and put them in a smaller room. So all these ones that have now been pushed outwards, we need to put them back inside. In doing so, I hope that what you can see is that an increase in pressure is very, very similar in its effect as an increase in concentration. So an increase in pressure causes a decrease in volume. But in doing so, you have caused an increase in concentration, which means you have increased the rate of the chemical reaction. As you can imagine, we can actually do this in reverse as well. It's going to be a little tricky because I had already drawn this about as big as I can draw it. But you can see squeezing particles closer together increases their concentration, which speeds up the rate by making more collisions, right? Think about the children. Squishing them together means they are going to be moving around the same speed, but with less space, they're going to collide more often. Let's think about this if we were to increase the volume, or in other words, decrease the pressure. So we need to expand this right out to the very edge of the screen so that there is absolutely no extra space left. Oh, try and keep it on the screen. And now if we think about those same 10 individuals occupying that space, they're going to be much more spread out. Making them more spread out, well, that's the result of our decrease in pressure or our increase in volume. And so now let's think about what effect this is going to have. A decrease in pressure is the same as an increase in volume, which is the same as a decrease in concentration. Look at how spread out they all are. They're not concentrated. They are actually very far apart. And that causes a decrease in the rate. Giving particles more space means they're less likely to collide. So think about my kindergarten children in a much bigger space. Like you put them in a big outdoor field, they're going to spread out from each other and run around, and there's a much smaller chance that they will actually collide. So this is how the pressure and volume can affect our kindergartners. We have one more example, and that is a catalyst. So what we're going to need to do is reset back to what we originally had. All right, so we've reset our room. You notice there's no children yet because I'm going to talk about what effect this is going to have, but we need to talk about what a catalyst does. So a catalyst is a special substance that you add into a chemical reaction. It is something that you add that actually regenerates itself back by the end. And it speeds up the rate by lowering the activation energy. So adding a catalyst lowers the activation energy, which actually speeds up the rate of the chemical reaction. They usually do this by actually forcing molecules to fit into shapes that force them towards a transition state. Enzymes in biology are actually all just a type of catalyst. They're a biological catalyst. So let's think about what this would be like if we had our kindergartners in the gym. The way that I've always thought about this is if you had some kind of sadistic person who was walking through the gym actually forcing collisions to happen. So this blue person is going to be our enzyme. And essentially what this would be like is if they grabbed one child, grabbed another child, and forced them to run into each other, causing them to become injured and therefore cry and react. I know it seems mean, but that's kind of what a catalyst is doing. It's working its way around, causing things to collide together, forcing them to react with each other, whether they like it or not. And in the end, they are unchanged. This person is still going to be able to walk around and roam around. And they can really only do this to a couple molecules at a time. But in doing so, they are going to speed up the rate of this reaction. So really, when we talk about rates, I think it's one of the few times that you can really see chemistry all around you. If you cook, if you do any kind of work with food, you get to see a chance to actually watch rates take place pretty regularly. And even if you don't, the principles are something that are somewhat intuitive because it's all about increasing the number of collisions. More collisions means faster reactions. And it's just understanding how the manipulating of different variables changes the frequency that things collide. So hopefully this helps you understand collision theory a little bit better, as well as the factors that can affect a reaction rate. So thanks for watching, and I'll see you next time.